Alright, welcome back. We are ready to work on problem 12 from Superquiz 1. So I've not put all of the instructions to this problem on the screen here, but the backstory, remember, is we were trying to predict whether or not there'll be a massive earthquake in the next 5 years. And what the geologists were saying is that if you could compute the area under a certain curve given by this function p, then that would give you a probability of there being this massive earthquake. The story said, well, if you wanted to get a good approximation, you really needed about 10,000 data points, but, well, we couldn't get that kind of data. We were able to get 9 data points, right? And that's because, well, getting these data points is expensive. Okay, so we're given a table of values. So it looks like we were able to, every minute, able to compute the value of this p of t. And so we want to compute the area under the curve at least between 9 o'clock and 9:08. All right? So maybe it would have been better if we could do this measurement every second or every millisecond, but we were only able to get them right every minute. So we saw before, right, using Simpson's rule typically is going to give us the best approximation of the techniques we learned. And thankfully, we were asked to actually use Simpson's rule. Right? So there it is, use Simpson's rule. So it's not asking us to use a left or a right endpoint, or midpoint, or a trapezoidal, but rather the parabolic approximation. Okay, so how are we going to do that? Well, this is where knowing the rule is very, very helpful. So we're going to be approximating. We're going to be approximating this integral. And so the first thing is we need to know what's the change in time for each interval. And in this case, well, you can see it's 1 minute. So we're just going to do all of our times in minutes, so it's easy. Our delta t is going to be 1. All right, so delta t is equal to 1, and then we divide by 3. All right, and now we need to evaluate p at our first time, and so our first time is 9 o'clock, but we don't want to write it that way, right? We want this to be time equals 0, and maybe this could be time equals 1, time equals 2, and so forth, right? And then our last one will be time equals 8. So we'll just take p of 0, and then we have to start this game, right, of alternating weightings, 4, 2, 4, 2, etc. So 4 times p of 1, 2 times p of 2. All right, and we're going to keep going. 4 times p of 3, 2 times p of 4. Of course, if you wanted to just dot, dot, dot this, that would be fine. 4 times p of 5, 2 times p of 6, 4 times p of 7, and then, oh, we're on the last one, and remember the last one, we don't get a 2 or a 4 weighting, we just get a 1 weighting. Okay, and so remember this delta t here is 1, and so now this is just simply a matter of writing down based on the table. We'll, let's see, so p of 0 is 0.12, 0.12, p of 1 is 0.05, p of 2 is 0.08, p of 3 is 0.02, p of 4 is 0.02, p of 5 is 0.02, p of 6 is 0.01, p of 7 is 0.02, and p of 8 is 0.03. Okay, so let's see if we can't compute these. So, well, here's something nice. We had a whole bunch of 0.02s. There's one here, and here, here, and here, so we could just add up the weightings now. So you have 4, 6, 10, 14 0.02s, right? So 14 times 0.02 is 0.28. So let's see here. We have 1/3, we have 0.12. Okay, 4 times 0.05 is going to be 0.2, so 0.2. Then we have a 0.02 times 0.08 is 0.16. Okay, then we said, what did we say? We had 14 of these, so that's 0.28. So 0.28. We have 2.01, so that's 0.02. And then we have a 0.03 with no weighting. Well, it's a 1 weighting. Okay, so then we can add this up. Let's see, this is 0.20. So we have 0.32, 0.48, let's see, 0.68, 0.76, 0.78, 0.81. So a third of 0.81 is going to be 0.27. Excellent. All right. So that would be our approximation that we have a 27% chance of having an earthquake, a massive one, in the next 5 years. Okay. What about part B? So part B is saying, well, we know there's some error, and what's the largest that error could be? So we're trying to put, all right, some bound on the absolute value of the error. And we know that this is bounded by, well, there was a formula we were given, right? So there was this m. We'll talk about that in a moment, right? B minus a, we got to know what those are, to the 5th power divided by 180 times n to the 4th. Okay, so that was the stated formula, and now we just need to identify what everything in here is. So the m, for instance, the m is the bound on the 4th derivative of the function, right? So that's actually what we were given, right? We were given a bound on the 4th derivative of the function, right? This is the 4th derivative of t, absolute value, and we're saying it's less than or equal to 0.01. So we can replace the m by 0.1. Okay, b minus a, that just comes from the interval. Okay, and remember we relabeled everything, right? So that it was for our times, right? We could do it in minutes. And we say, okay, that's just an 8-minute difference. So b minus a is just 8. So this will be times 8 to the 5th power. Okay, 180. That's a number. We can write that down. And then n is actually the number of intervals. Right? Well, we had 8 intervals, right? There were 9 dots, right? 9 data points. So we have 8 intervals. So this is times 8 to the 4th. And hey, that's actually pretty nice because we have 8 to the 5th over 8 to the 4th. So most of those will cancel, and we'll just get a 0.8, okay? So that's 0.1 times 1 copy of 8 divided by 180. All right. If we wanted to go a little bit further with this, we could recognize 0.8 is 8/10. So I could rewrite this as 8/10 over 180, or 8 over 1800. And if I wanted to simplify, let's see, we'll cut it in half and we get 4 over 900, 2 over 450, 1 over 225. So if 1 over 100 is 0.01, then 1 over 200 would be 0.005. So this is even less than that, right? So we know our error is going to be less than 0.005. So not too bad, right? This is actually a pretty decent approximation. And there we go.